Hey everyone, welcome to the second lecture in Unit 3, U of W Chem class. This is dealing with thermochemistry, and first unit we looked at Q, heat. This first lecture we looked at Q. Second lecture, which is right now, we're going to look at work and the relation between work and heat. Just before we start the work though, let's try an example from the textbook. So I'm going to go to, let's see here, Alt-Tab, to an untitled fresh page here. Tab, tab, tab. There we go. And I'm going to get the pen. Here we go. This is page 159. And this is example 3.15. And what it says is a silver coin, so silver, I'm going to need the molar mass of that. Silver molar mass is, looking upside down here, Ag 107.87 grams per mole. So I have 27.4 grams. And I'm going to get some moles, and then I can use the molar heat capacity for silver. So again, silver is 107.87. 2 decimal places for molar mass is always good enough for this class. Grams per mole. So 27.4 grams divided by 107.87 is 0.254. Good enough. 0.254 moles of silver. It's heated to 100 degrees Celsius, so the initial temperature associated with the silver is 100 degrees Celsius. I don't have to convert to Kelvin here. Talk about temperature differences, so I can keep it in Celsius. Then it's dropped into 37.5 grams of cooler water, not boiling water, but cooler water, initially at 20.5 degrees Celsius. So the water initially is 20.5 degrees Celsius. And the mass of the water is 37.5 grams. So the question is, find the final temperature of the coin in water, right? So you're putting a hot coin into a cold cup of water, not cold, room temperature. So when they reach thermal equilibrium, the temperature is going to be somewhere between 100 and 20.5. My guess is it's going to be closer to the 20.5 than the 100 because water has a higher heat capacity. If I want to find the heat capacity of silver, I got to look that up. And let's find that one here. We have a chart. I know. You can look for it in your table as well. I don't have enough desk space here. The dog is sprawled on the table. There's silver, 25.351. So the molar heat capacity of silver is 25.351 joules per mole per degree. Okay, and for water, I'm going to need that 75.291. Joules per mole per degree. I guess I'm going to need the moles of water. So that's 37.5 grams over 18.02 grams per mole. 37.5 divided by 18.02. And I get 2.08 moles of water. So I'm setting it all up. Now, how do we do all this? We do all this by just thinking that the heat flow from the hot silver, the heat lost, is the heat gained by the water. So think of the silver as the system and the water as the surroundings. There's going to be Q values which are going to be opposite to each other. And that's how it's done. And Q is mc delta T. So the mass, or NCM delta T. So the moles of silver is 0.254 times 25.351 times T final. That's what we've got to solve for. The initial temperature is 100. Equals minus the water is 2.08 times 75.291 times T final minus 20.5. Okay, so now we've got to solve for T final. So I'm going to multiply these together. I'm going to need a new page, aren't I? Okay, 0.254 times 25.351, 6.439 times T final minus 100 equals, and then I'm going to do 2.08 negative times 75.291 minus 156.605 times T final minus 20.5. Okay, so then the 6.439 divided by 156.605 minus 0.0411. I'm going to go way up here, so you don't have to go on to the next page. So minus 0.0411, and you might do it in a different order, just get the right answer. T final minus 100 equals T final minus 20.5. So now I can distribute the minus 0.041 into both parts. So minus 0.041 T final plus, so 0.041 times 100 is 4.1 plus 4.1 equals T final minus 20.5. And then we collect the like terms. So we've got a T final plus a 0.041, so that's 1 and a 0.041. So 1.041 T final equals, and then I got a 4.1 plus 20.5. 4.1 plus 20.5, 24.6. So then T final will be 24.6 divided by 1.041. I get 23.63. Okay, which is more than 25, but not much more. And you can find that answer. I have to go all the way to the end of the book for those. Answer to section exercises, answer to practice exercises. Yeah, and you have the solutions also in your wu3lec2 booklets. You have those as well, those solutions. So if I'm going to find it here, as you look at here, this is an odd number problems, right? 3.15. 15 is an odd number, right? Chapter 3. 15. 23.6 degrees. Hooray, I got it. And you can get it too, okay? So you practice it, you make sure you get it. And then there can be variations of questions associated with that. Okay? So now let's Alt-Tab and go to the mini text here. And we can talk about work. And work is force times distance. And let's get to the important part. When a system, when a system does work on the surroundings, the sign of W is negative because the system loses energy. Okay, so W stands for work. When the surroundings do work on the system, W is positive because the system gains energies. And that is just the convention that we are going to use for work. So there's a transfer. The work of the surroundings is the negative the work of the system. So now we can put that together and look at what's called the first law of thermodynamics. Because energy is exchanged in only two ways, as heat or work. For example, when gasoline burns in an automobile engine, some of the energy released does work in moving a piston, and some of the energy heats the engine and is lost to the surroundings. So the change in energy, sometimes called the change in internal energy, is Q plus W. Some books write it as delta U equals Q plus W. So you see sometimes instead of delta E, you say it written as delta U. And so you see that the change in energy of the system equals the change of energy of the surroundings, but there's a negative sign, right? So what is lost in one energy transformation is gained in the other. So what we're saying is that energy is conserved. Okay? So this is not that useful here. We do talk about state functions and path functions. The only path functions we're going to look at are Q, W, and distance traveled, which we really don't talk about much. But a path function depends on how you get from one place to another. Not just on the initial and the final point, but how you get there. Like displacement is a state function because it only depends on where you started and where you end. All you physics people know that. Pressure, volume, temperature, those are state functions. The difference just depends on what's your final temperature compared to what's your initial. But think of work as being like, or heat released as being almost like friction. Like you take a chalk brush and you move it all over the board and you're causing some heat to be emitted, and how you move it around the board is important. The path you take is important. That's why Q and W are called path functions. So they depend on how the change occurs, whereas state functions depend on just where you start and where you end. And you can look at that distance example yourself. I think it's a bit of an overkill there. Okay. So let me just keep going through here. Again, I think some of this stuff is too much detail for what we need to know. And so I'm going to not to talk about it quite yet. Let me do some number crunching with the delta E equals Q plus W. And I'm going to go to a PowerPoint slide from an older textbook that I sometimes use, and I can give you the pertinent information. So let's go Alt-Tab, and okay, let's go here. I'm going to enlarge this a bit for you so you can see better. How do I get to there? Is that going to work? Oh, there you go. Wow, I got more windows open than a bakery on a hot summer day. Gosh. Okay, so relating delta, U, Q, and W for the first law of thermodynamics. A gas while expanding, and when gases expand, they do work. It's called the work of expansion. Absorbs, again, don't worry about those numbers there. Absorbs 25 joules of heat and does 243 joules of work. What is delta U? Delta U is also delta E. So delta E is Q plus W. Q is saying it's absorbing heat, so that is positive. So it'll put brackets there to emphasize that. So the absorbing heat is 25 joules. Work is done by the systems on the surroundings. That is what we mean by work of expansion. So negative 243. So 25 plus negative 243 is negative 218 joules. So we are getting a overall loss of internal energy of negative 218 joules. Okay, so that's one system. Let's try another one here. I think I'm going to go to the make it a presentation so I can use, oops, how do I get it so it's, okay, it's an old system there. Okay, so I just wanted to write something in there. Okay, well we'll just remember. You'll write it out. Okay, so let's go to notes. No, that's not going to work. Click to add notes. Oh, I can type in, fine, okay. So in practice example A, in compressing a gas, 355 joules of work is done on the system. So W equals 355, and at the same time 185 joules of heat escapes. So Q equals negative 185. So they want to get work. No, they got work. So we want to get delta U, or energy change. Delta E equals Q plus W. So minus 185, 185 negative plus 355, 170, and those units are joules. Okay? Now practice example B. If the internal energy of a system decreases by 125, so delta E is negative 125 joules, at the same time that the system absorbs 55 joules of heat, so Q equals 54. Does the system do work or have work done on it? So work is delta E, sorry, work is Q minus delta E. Work equals Q minus delta E. So Q here, so it's 54 minus 125, right? So that's going to be 54 plus 125, which is 179 joules, which means work is done on the system. Okay, so that's all captured there for you, and that's an example of numerically handling the first law of thermodynamics. Sometimes the book we use leaves off stuff that still appears on tests, so I want to make sure to fill in those portions so that you aren't surprised when tests come around. And sometimes in your online assignments you'll see a few questions that weren't discussed that much in the textbook. So sometimes you do have to look around, and the Petrucci textbook is a good one, and that's what I was using for those questions. Another thing we talked about, I might as well talk about it now since I have these slides on here, is I mentioned a bit already, the work of expansion. Okay, so here we have pressure versus volume work, pressure and volume. So it turns out that the work done, if there is a gas involved and the gas changes in volume, then the work, I'm not going to worry about this calculation, I just want to look at the equation here. The work is minus P external times delta V. Okay, well, maybe I will look at this question here. Suppose you have a gas which is 0.1 molar helium at 298 Kelvin. The two weights correspond to an external pressure of 2.4 atmosphere. And then it goes down, you lift a weight on some expansion apparatus to decrease the external pressure to 1.2. How much work is associated with the gas? Okay, so you have an initial volume. You may have in grade 11 looked at PV equals nRT. We will look at that again in this course. So you plug those in and you start at 2.4 atmospheres. So you have 1.02 liters of helium. Then you expand that to 2.04. So the gas is expanding, which means work is done on the surroundings. and your work has to be negative then. Your change, well, not your change in external pressure, it was working against an external pressure of 1.2 atmospheres. Okay, it was working against it, that's given. So work is minus 1.2 times 1.02, which is the change in volume. So we have a fixed external pressure given has 1.2 atmospheres. The change in volume is 1.02 liters. So you multiply that together, then there's a conversion factor. Usually we don't leave things in liters atmospheres, we convert them to joules. You would be given that conversion factor, that 1 liter atmosphere is 101 joules. So you multiply that all out and you get work of minus 124 joules. Okay, so that's how that works. That's funny. I made myself laugh. Okay, let's try another one of these. Practice example A. How come I cannot seem to get down onto this one here? There you go. How much work in joules is involved with 0.225 moles of nitrogen at a constant temperature of 23 is allowed to expand by 1.5 liters in volume against an external pressure of 0.75 atmospheres? Hint, how much of this information is required? Well, here's a question where TMI, we got too much information. So we just want to get the work. So the work is minus P external. The external pressure is 0.75, so minus 0.75 times 1.5. So 0.75 minus times 1.5. And we get minus 1.125 joules. Okay, so, no, sorry, that's not minus 1.125 joules. That's minus 1.125 liters atmosphere multiplied by 100. And then we get minus 111, sorry, minus 112.5. So you are expanding against an external pressure. The volume is going up. So the work has to be negative, and it turns out to be negative 112.5 joules. Okay, I'm not going to bother with the next question. But so that's a work of expansion example. And there you have it. Okay, let's get out of that one and continue on with energy changes in chemical reactions. So we have here, this in your textbook is on page 125. And let's see, I haven't looked really much at our slides, have I? Let's go to our slides for a second. Okay, why don't we look at this? These are the slides for a bit of variety here. So if you want to break a bond, you need energy, just like you know, in karate, when there's a board and you want to break that board, you have to chop that board up. So bond breakage requires energy. Glue it together, that releases energy. It's like you're locking something in place. Those drawings I never find helpful. If you do, go ahead and use them. Okay. So let's look at some numerical examples involving energy. Here is the Haber process, and if you want, on my All This Science podcast, someone did, I forget the name, whatever, probably someone in this class right now, did a great podcast on the Haber process, and you just look it up, All This Science, coming to a podcast near you. So the Haber reaction for the formation of ammonia releases energy. So there can be rearrangement of bonds, bonds breaking, bonds forming. Overall, an exothermic reaction happens because delta E is negative 40.9 kilojoules. Now some of you are going to say, oh, but that's not exactly the same as delta H. No, it's not, but it's close enough that you aren't going to change from the conclusion that this formation, this is actually called a heat of, well, no, almost, it's forming 2 moles of ammonia. This is an exothermic process. So the question says, how much energy is released in the production of 1 kilogram of ammonia? Okay, so let's go to the text here. And we see that, wow, look at all the flow charts just to do this one question. Okay, that's fine. Link the mass of the product with the energy released. We must determine the number of moles of ammonia and take account the coefficients in the balanced equation. Okay, so the number of moles of ammonia, how much energy is released in the production of 1 kilogram? Okay, so the number of moles. So N is moles. What file am I in here? Why is that? Okay, lowercase n stands for number of moles. M is the mass in grams. And then the italicized M is molar mass. Sometimes the book changes, and sometimes that italicized M is used for molarity. But for now, that's going to be molar mass. Sometimes I just write out the word molar mass. So moles is the grams, so 1,000 grams or 17.03 grams per mole, 58.72 moles of NH3. Use the stoichiometric coefficient for NH3, the number in front of the balanced equation, and delta E to determine delta E molar. Like per 1 mole of ammonia, well, it was 40.9 kilojoules released for every 2 moles of ammonia, so that is 20.45 kilojoules released for every 1 mole of ammonia. So how much energy is released overall? You're going to take the minus 20.45 kilojoules per mole times 58.72 moles, and you get minus 1.2 by 10 to the 3 kilojoules. The more stuff you have, the more energy is released. The more stuff created, the more energy is released. Okay? So that's okay. Shall we try this example here? Why not? Acid-base neutralization reaction. Calculate the energy change when 25 mils of 0.1 molar HCl reacts with excess NaOH. So HCl gives me the H3O+, NaOH gives me the OH-. You remember that from grade 12 class. So let's see, I want to get moles. So moles is molarity. I'm just going to write out the word times liters. So it's 0.1 molar times 0.025. So it's 0.0025 moles. Okay? So I know that if 1 mole of ammonia is going to react with if 1 mole of hydronium ion is going to react with 1 mole of hydroxide, I'll form 2 moles of water and 55.8 kilojoules will be released. Here I am having 0.0025 moles of H3O+. Molarity is moles per liter, so moles is molarity times liter, good, times negative 55.8. 0.0025 times 55.8 negative 0.1395 joules. Okay, so that's not joules, that's kilojoules. Be careful there, right? I didn't convert to joules anywhere, did I? So energy change, I can leave it in kilojoules. If I asked to do it in joules, well then I'd have to multiply by 1,000. So let's look at the end of this chapter and look at practice exercise 3.3 and see if we got that one right. Again, the practice exercise answers at the end of the chapter. Minus 0.14, yeah, good enough. Some of you may want to photocopy your sets of answers so you aren't flipping back and forth all the time. And you can do that if you want, however you want to organize things. And here's something I talked about before. If you're saying, I need a bit more practice with this energy stuff, well, look, it says right here, need more practice, try these problems. So these problems, 3.21 and 3.22, are at the end of the chapter. Let me just go up a second here and see if there's any other important things that you may have forgotten when we're talking about some features of reaction energies. I see here I have a 2NO2 goes to N2O4. That is forming N2O4, and in this example, all things said and done, this is delta E is negative 52.8. We say this is the equation as written, going from left to right. If I go from right to left, N2O4 goes to 2NO2, then I get positive 52.8 kilojoules. Okay, so if you write the equation in the opposite direction, you just change the sign. Okay. Here, we're writing what we start with. 2NO2 goes to N2O4, delta E is minus 52.8 kilojoules. If I have 5 times as much of the NO2, give me 5 times as much of the N2O4, then the energy released will be 5 times as much. Okay, these kinds of properties these are called extensive properties. So delta E is extensive. So if you're writing it as 10, which is 5 times 2, then the energy released is 5 times as much. Okay? And there was our example 3.3. And so that's good. Path independence, I don't care much about that. On its own, I mean, built in it's okay, but on its own, it's not such a big deal. So our last topic in this lecture is going to be about bond energies, because we're talking about breaking bonds and forming them. If you wish to use the path that breaks molecules apart into atoms, we must imagine breaking chemical bonds. Chemical bond is a stable arrangement of electrons shared between the bonded atoms. Therefore, a bond cannot be broken without an input of the bond energy. Be italicized is what we'll use for bond energy. They're positive quantities because a molecule must absorb energy to break its chemical bonds. Bond energy is expressed most often in units of kilojoules of energy per mole of bonds. So, for example, we have hydrogen here. To separate 1 mole of hydrogen molecules into hydrogen atoms, you have to pour in 435 kilojoules to break those bonds. If we were forming a hydrogen molecule from moles of hydrogen atom, 2 moles of hydrogen atoms, we would be releasing 435 kilojoules per mole. Now, this is these numbers are rough and depend more on the specific molecules, so they're really averages. And anyways, we see some examples of the tables, and they're tabulated in this table on page 129. All values are averages, right? The values are give or take 5 kilojoules per mole, and each value is the energy per mole required to break a gas molecule. If it's not gas, then you have to add more stuff to it. You have to talk more about other attractive forces. And even single bonds, double bonds, triple bonds have different stories. So for example, carbon-carbon single bond is 345. Carbon-carbon double bond is stronger, 615. Carbon-carbon triple bond is stronger 2 at 835. So 345, 615, 835. So it's harder and harder to break the bonds the more glue that's present between the atoms. Okay. So let's just jump straight into the equation. There's a big buildup here, but if we want to get delta E reaction given these bond energies, here is the important equation. So again, you can read the buildup, but this is what it is. You add up all the bonds that are broken, the energy needed to break those bonds, and you subtract from that all the energy released when bonds form, and that gives you delta E. It might be positive, might be negative. You just have to use the table and plug in those values. So here's an example. We have a combustion reaction, which we know is going to be exothermic. Always giving you carbon dioxide and water, sometimes water vapor, sometimes liquid water. Here we have water vapor. So we have C3H8 plus 5O2, so this is propane and oxygen, giving me carbon dioxide and water vapor. So I got propane here. I got one carbon-carbon bond, another carbon-carbon bond. So I got two carbon-carbon bonds, and I got 1, 2, 3, 4, 5, 6, 7, 8. 8 carbon-hydrogen bonds. Okay. So I'm going to add the energy associated with a carbon-carbon single bond 2 times, a carbon-hydrogen bond taken 8 times. So that's going to be part of the bonds to be broken. Remember, this is the symbol for sum, add together. And then I got oxygens. Well, I'm breaking 5 oxygen-oxygen double bonds. Okay, then on the other side, I'm going to add the values for the carbon oxygens, and there's 6 of those, and then water, well, there's 2 OH bonds in each water, but there's 4 water, so that's 8 OH bonds. So now you just add up the numbers. It's almost like doing your taxes. So your bonds broken, you get 6485, bonds formed, 8480, and then you just take the 6485 minus the 8480. Now there's other ways to do this where you start switching signs in the middle. I don't like those ways. I think the way in the book here is done very clearly. You just make the tabulated values using table 3.2, and then all the stuff on the left, add that together, all the stuff on the right, add that together, and then do left minus right. So the delta E of the reaction is minus 1995 kilojoules. It turns out accurately to be minus 2044, so it's off by just 2.5%, and that's because we're using average bond energies in table 3.2. But that's a pretty good estimate, so so that's good. Okay. Okay, you can read about fossil fuels if you want. Let's look at this example here, example 3.4. This is on page 132, and we have here ethylene and hydrogen chloride and oxygen gives you vinyl chloride and water. Based on average bond energies, what energy changes comes the formation of 1 mole of vinyl chloride? Oh, okay, so we're going to do it with 2 moles, and then at the very end we'll divide by 2 because they want 1 mole. Okay, so CH bonds on the left hand side, I got 4, but 2 times 4, so 8 of those. 2 of the CC bonds, 2 of the HCl bonds, 1 of the OO bonds, and I don't really need an atom inventory, do we? Bonds formed, I got 6 carbon hydrogen, 3, 6, yeah, and 2 CCls and 2 C double bond C and 4 OHs. So I add these all together, and I'm going to get 5905 minus 6220. So I get a delta E of minus 315 kilojoules. So this is an exothermic process. And I'll let you try practice exercise 3.4 and the problems on your own. Something I haven't talked about before is section exercises. Sometimes those are helpful for us to do together. Sometimes most of the time they're helpful for you just to try on your own. And as section exercises, those answers are written. Now, are they written in the back of the... they're written at the back of the chapter, not at the back of the book, but at the back of the chapter. Okay, so you can try the section exercises on your own, and that gives you a stronger reinforcement of what's going on. Okay, so let me go to the PowerPoint and see if there's something else helpful. Bond energies, table bond energies, reaction energy. My delta E is the sum of the bonds broken minus the sum of the bonds formed. There's some examples that we looked at. So our next topic we're going to focus will be on calorimetry, and that will certainly generate some heat. See ya.